I am recording. All right, let me make sure this is on the screen too. Okay. Hello. Greetings. Welcome to Unit 9 with Mr. Heller. No. What if that's what I talk like? I would just fall asleep. Do you have like a teacher in your day that has just a relaxing voice that like will put you to sleep almost?
No, I'm just sleeping because I'm tired and bored.
Coppola has a English teacher accent every day.
Mr. Klein's accent.
She has a relaxing voice. I can see that.
It's definitely, it really is like that.
All right. Tyler's mad because I didn't play this song today. Because, like, it's the final countdown. Ba-da-da-dum. Okay, all right, I'm done. Da-da-da-da-dum. I actually did it like the whole, yeah, okay. All right. What can I not do? That's the question.
Basically David Hasselhoff at this point.
I'm basically David Hasselhoff. I have a car that talks to me. No, I don't.
You have a scooter dog.
A scooter? No, it doesn't. It doesn't even have, I just push it with my legs.
Just put a speaker on.
Anybody seen me scootering yet?
No.
I haven't even seen you. I'm surprised.
I know, I thought I would have seen it at some point.
I'm picking up Avy today at 3:30 on the scooter, so at Keene. Okay.
Cat with me.
I parked my scooter down the path on this little fire hydrant right across the road when I walk over to Keene to get her. And we scooter to my parents' house. So, all right. Wow. We have wasted more time. Welcome to Unit 9. All right, are we recording? Okay, we are actually recording. Okay, what is entropy? We've mentioned this, right? Lots of times. So, entropy, we've talked about it, is what? Chaos. Disorder, yes. So, this class, sometimes. One may assume that a reaction with a negative delta H value would always proceed. Why? If you have a negative delta H value, you are what? Exothermic. Because that would mean that the products, agreed, will have a lower energy than the reactants. Which means they became more what? If it gave off energy, they became more stable. They became more stable. But once again, that's not always true. That's not always true. If a reaction has a very high activation energy, that's the hump that you got to get over, right? It will not occur. It will not occur and is described as kinetically stable. Kinetically stable or under kinetic control. In this case, one may predict that the reaction would produce very little products. I'm not saying none, but it's very heavily favored to the left. Great. Actually, this is actually pretty easy compared to what we just did. So like Unit 8 was the hardest. This is actually pretty easy. One example would be the oxidation of ammonia by oxygen gas to produce nitrogen monoxide and water. The delta H for this reaction is negative 909 kilojoules per mole. That is massive. Kilojoules per mole, showing that ammonia and oxygen are very unstable. But the reaction actually doesn't proceed. Why not? The activation energy is so high. Yes. The activation energy is so high. Therefore, the reactants are considered actually stable, and nothing will happen until that activation energy is met.
Which is very, very hard.
Yes. One would also assume that reactions with a positive enthalpy will never proceed, since the products have a higher enthalpy. The products have a higher enthalpy than reactants and are less stable. But this also doesn't hold true. We know we've seen reactions that felt cold, right? It does happen. This means that delta H and activation energy are not the only factors that determine whether a chemical reaction will or will not take place. So there has to be something else going on here, which we're going to talk about. So here's an example. Potassium chloride dissolving. What would be the simplest way to write that in equation form? KCl, which is a solid. What am I going to add to that? Water, which is a liquid. We're just going to draw this one way right now. We don't really care about equilibrium at this point. What's that going to make? KCl aqueous. Now, we know that there's ions floating around, yes, but it's KCl aqueous. The delta H for this reaction is positive 19.2 kilojoules per mole. But it happens, all right? And that would feel how if you touched it? I'd feel cold. By looking at the above equation, we see that there's a change from the relatively ordered, or I want to also say organized. Let me try to zoom in just a little bit more. Solid to a less ordered or disorganized state, which is a solution. The degree of dispersal of energy in a reaction is called entropy. So entropy is the degree of dispersal of energy, or the chaos, or the disorder. That's entropy. And the symbol we use is S. I don't know why, because probably we already use E for energy and everything else. So like, okay, we're running out of letters here. Why not S?
Until we were using one that's also super used.
I know. In the reaction above, there has been an increase. There's been an increase in entropy. Would you agree that my entropy has increased?
Yeah.
Why?
It's a result of water.
Yeah.
Well, I took a solid, right,
So
and a liquid, and I ended up with
the solution.
a solution. So solid's more ordered, agreed?
Yeah.
So I have an increase in entropy, which means the matter has become more dispersed. More dispersed, yeah. And therefore, my delta S, which is my change in entropy, okay, is positive. The hardest thing about what we're going to be doing is just keeping your signs straight. Because there's going to be three different things: delta H, which we already know, delta S, and also delta G. So keeping the signs straight will be the hardest thing, and it's not going to be that bad. The universe always tends towards entropy. How do we have proof of that? What's the universe doing right now? Expanding, right? Would you agree that that's more disorder? Yeah. It's more everything, but it's also more disorder because it's getting more spread out. It's just like your bedroom at home. All right? If you do nothing to your bedroom, what will happen to it? It gets messy. The only way to get more order in your room is by putting what into it?
Work.
Energy. Work. Yes. So the only way to get entropy to go away is by putting energy into the system, which my daughters never want to do because they're 5 and 7. But if you bribe them with a Pez, maybe they will.
I think that only works for me.
What? Only one of them? Yeah, you're right. Avi be like, "Can I read a book?" Like, sure. Yeah, she loves reading. Well, Jovi can't read yet, but anyways. Does that make sense though? Okay. A pure, this is kind of cool. A pure, perfect crystal at 0 Kelvin, aka what? Absolute zero. At absolute zero would have 0 entropy. Is that possible?
No.
Not that we know of. Right? Because the crystalline structure is perfect, yes. And absolute zero means my particles aren't doing what? They're not moving. So if I could get a pure crystal at 0 Kelvin, that would be 0 entropy. Does that mean that 0 entropy is possible? Not yet. All right? Not that we've been able to do as humans. We've gotten close. But to get 0 entropy, it's basically impossible. So 0 entropy, or we would say that is completely organized or completely ordered. All entropies in the real world are measured relative to this, which means all values of delta S should be greater than 0. So that's my change in S, right? So there has to be some kind of base. Now that the value can still be negative or positive, but the change has to be greater than 0. Now, I add this little thing down here. Aqueous ions are measured to actually a relative different 0. So they could have negative values, but you're not going to see that on the AP test. I just want to throw that out there for funsies. It's weird. We don't have to worry about that. Okay, flip the page. We have a box. Guess what we're going to do with the box? We're going to write stuff in the box. Yes. I know. It's crazy. So let's talk about how entropy works. The change in enthalpy my delta S for solids, is going to be less than my delta S for what? Liquids. Agreed? You'd agree that liquids are less organized? Which is going to be way, 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 way less than gases. Yes. Than my delta S for gases. Because remember, solids, right? Vibrating in place. Liquids, just sliding past each other. Gases, crazy. That's why it's way, way, way less. That's one. My delta S for a low number of particles, or my entropy for a low number of particles, is going to be less than what? A delta S for a high number of particles. Ooh, I almost wrote delta H. Oh, great. Now it looks like a money sign. Delta S for a high number of particles. Can you think of any other examples how I can make delta S different? Temperature. My delta S increases. My delta S increases with the increase of temperature. Because we have defined temperature as the average what? Kinetic energy. So we're saying that the particles move how? The particles move faster at a higher energy. There's one more. What else could affect my delta S? This is only with gases.
Container size?
Yes. My delta S of gases at a small volume is going to be what? Less than my delta S of gases at a large volume. Because in a large volume, what can my gases do? They can expand, right? They can expand. And when they expand, there's more disorder. Cool? So, we're going to look at these, and we're going to see if these are becoming more ordered or less ordered. We're going to say what the sign's going to be. So, number one, 1A. Would my delta S be negative or positive for number one? 1A. What do you guys think? It'd be negative. Why?
You're getting rid of a liquid and making it more solid.
Exactly. I'm taking a solid and a liquid, and I'm ending up with only a solid. Yes? So this became more organized. What about B? Positive. Because B, now I have a what in my products? Which is way more what? Disorganized. There's more entropy. Cool? Questions so far? Tyler, how you doing? Okay, great. All right, so then number two, take a second and circle the correct one in each one of these. Circle the one that has greater entropy in each of those situations. Since I've been eating way more healthy, I brought back Fun Breakfast Friday today. I told you about this before, right? No. Some people know about it. So I usually don't eat breakfast at all, but on Fridays I'll let myself eat whatever I want. Had Oreos for breakfast.
Oh, you never said the name of it. I think you mentioned it.
Fun Breakfast Friday is what I call it, yeah.
That makes sense, yeah.
Yeah. And then we also have cereal Saturday at our house, but I usually don't eat breakfast. Mostly because I eat lunch at 10:30.
Yeah.
So it just messes up everything.
I don't have breakfast either.
It's like brunch, is what I call it. Should teachers get free lunch at school?
Yes.
Well, here's the thing.
Why?
Everybody should.
I agree with that too.
Like,
It was during COVID, we had a grant. I don't know. I'm asking you guys. You guys are like the ones who like debate things and are like on the newspaper. Maddie says yes. Why? Why should teachers get? You said yes.
Y'all already work here and
Yeah.
provide a service. They don't
That's
need to-
kind of what I
Like
think.
an extra.
Like they don't.
Like I like basically live here 8 to 10 hours a day. I don't know.
Then you
I feel like
work
you could-
outside of it.
I mean, it's not like,
Like
and it's not like a crazy thing like doctors in a hospital who work like 12-hour shifts get their meals free.
they also get paid a lot more.
Yeah.
Yeah, they also get paid a lot more.
Yeah.
So that's what I'm saying.
I mean, I'm just saying that a meal is like $3 a meal. and I don't think all the teachers would even take advantage of it.
No,
So we have like, let's say 100's high. We probably have 80 teachers in this building. 80 times 3 is $240. I don't think 80 people would eat a meal here a day.
Yeah, you're probably looking at max.
Maybe 30. That's $100 a day.
I'm just saying that.
Times 180 days. That's like 18 grand. That's not a lot of money compared to like our budget. I don't know.
The fact that we managed to privatize food and water in the first place is kind of messed up.
Yeah, no, yeah.
I don't know. Why was I talking about that? All right. Oreos for breakfast, yes. Okay. Tyler M. Which one did you circle for the greater entropy for A?
400.
Metal at 400. Why?
Because it's a higher temperature.
Particles moving faster.
Look at that go.
Tyler H. B. What'd you say?
Soft metal.
The soft metal like lead. Why?
Lesson, please.
Less in place, less organized, not a crystal structure.
My voice gets big.
I know. He threw his voice over to Aiden. All right. Jackson, what'd you say for C?
1 ATM.
The one with 1 ATM?
Yeah.
It'd be 0.5 ATM. You want the lower pressure, right? If it's 1 ATM, what have I done with it?
Oh,
I've compressed it so the particles are closer together. The lower pressure, more room to spread. More room to spread. So the change in entropy, which we use S with that little, you guys remember what this little 0 means?
Degrees?
Nope.
Oh, well,
Standard conditions, remember that?
no.
When we solved for delta H, we had this. When we had bond energies, we had this. In a reaction can be found by subtracting the sum of the absolute values of the entropy of the reactants from the sum of the same for the products.
So it's just like finding delta.
It's the same equation. So delta S standard is equal to the sum of S of the products minus the sum of the S of the reactants. So you'll take your number of moles of products, multiply it by the entropy, add it up, subtract. This is a good point to review. So, by the way, delta G, which you're going to see in a second, is also products minus reactants. There was only one equation that was reactants minus products that we used this year. Does anybody remember what that was? No. Hydrogen bonding? No. Maxwell-Boltzmann? No. Bond energy. Because remember, bond energy was bonds broken minus bonds formed.
Yeah.
That's the only one that was reactants minus products. So, just something to remember. I thought about that second period. I want to bring that up here too. Cool? That had nothing to do with this. Just a little review. Okay, so try it. Use this to do this. Remember how these are in the back of the book in that table? Remember the table where you had to look up the delta H's? I've given it to you here, so you don't have to use our book. So do it. Take a minute, do it. The reason, something that as you guys are working, you'll notice that elemental form is not 0 anymore. Right? Why not? Does elemental form have some kind of order for entropy?
No.
Yeah, there'd be some kind of entropy, right? Yes. So elemental form for entropy does not necessarily mean 0 automatically. How do they measure it?
Yeah, how do you measure entropy?
It's all based off of absolute 0. So they like figure out like the different densities, the masses, what they do at different temperatures. Well, the units are actually weird.
Joules per kilomole. Is that kilomole?
No, this is actually joules per Kelvin mole.
So this is like specific heat.
Yeah.
And
In a way.
Unit-wise. Whereas joules
In a way.
divided by a temperature and a
Yeah, but
volume.
specific heat was joules per gram degree Celsius.
Yeah.
So this isn't really like that. It's just a different unit.
Oh, no, I mean unit-wise.
Yeah.
How the units work.
All right, you guys do that. I'm going to do my work as you guys are doing your work. So delta S equals 2 moles NH3 times 193 joules per Kelvin mole minus 1 mole of N2 times 192 joules per Kelvin mole plus 3 moles of H2 times 131. Did anybody get an answer?
-1.
I got negative 199. What are your units?
Joules per mole.
Kelvin.
Joules per Kelvin. It would just be negative 199 joules per Kelvin. So, this is weird because the majority of our units are in what so far? Not joules per mole. It's usually what? Kilojoules per mole. So guess what we're going to be doing eventually? Yep, converting. We could have predicted this, right? We could have predicted that this value was going to be negative. Agreed?
Yeah.
Because the system became more what? Ordered. The system became more ordered or less dispersed, however you want to say it. I think it's easier just to talk about order than dispersion. So this means that 4 moles of gas turned into what? 2 moles of gas. 4 moles of gas turned into 2 moles of gas. So we're going to start combining this with the stuff that we already know into one new big equation. So enthalpy and entropy are brought together in the Gibbs-Helmholtz, which sounds like a ketchup, doesn't it?
Yeah.
I don't know why, but it sounds like ketchup. Free energy equation, usually just hear Gibbs. And here's the equation. Triangle G at standard conditions is equal to, what? G for Gibbs, yes. Is equal to delta H, which is your heat of enthalpy, minus Kelvin temperature, T, times your enthalpy. So, what we're solving for here, the G is called spontaneity.
That's the word, yep.
Yes. Is a reaction spontaneous? What does that mean if a reaction is spontaneous? That means once it starts, it keeps going. Once it starts, it keeps going.
So when they were doing the Manhattan Project and were trying to find out if like the reaction would just not stop in the world, they probably did this equation.
Yes. And we're going to see how and why in a second. What do you got there?
Some cheesy popcorn.
Where'd you get that?
It was like in a giant bag in the staff lounge,
Oh.
but there wasn't much left.
Oh, so a lot of people's hands have been in there.
Well, I'm assuming a lot of hands. But the problem was I wanted the whole bag.
So did you take it?
No, because there was people in there.
Ah.
So I was like, oh, I'll take this little plate.
But really, you're sacrificing for other people because other people had hands in it. So you're helping people not get germs.
Exactly.
I like that shirt.
Thanks, man.
Did you try to wear Worcester colors today?
No. Well, first off, I don't pick out my clothes. Katie does. Um, so this is what was there.
Okay.
You know.
He's not kidding.
I know he's not.
Huh?
I know.
You pick out your own clothes?
I do.
I love
Yeah.
to tie loose.
I do.
I know Mr. Ruff does. I know.
All right.
I know that's.
Wait, is that his wife? If it's-
Uh-huh. Yeah. It'd be weird if it wasn't his wife. Huh?
On my notes now.
Yeah, it was. I'm glad people in Washington D.C. heard that.
Shout out DC True.
In order, yes. We hope all you people on the bus are having a great 6-hour bus ride. Say hello to some politician for us. Bye. Why did I say bye? We're still here. All right. In order to apply this equation, all reactants and products in an equilibrium. So equilibrium is not going away, which I was thinking about. How crazy is it? It feels like we just started Unit 7, and here we are at the end. Here we are at the end. Must be at their standard states. And if you remember what standard states are, that is at 1 atm, 1 molar, and the temperature is what for standard conditions?
298.
298. 298 Kelvin, which is room temperature. Room temperature. Entropy values tend to be given in units that involve joules. But enthalpy, I hinted at this, is usually given in kilojoules. This means you got to do some conversions in order to get your delta G, right? Easy though. All thermodynamically favored, I'm going to put in parentheses spontaneous chemical reactions have a value for delta G that is negative, which is a little bit weird. So if it is a spontaneous equation, it's negative. That's why I said the hardest thing about this is keeping your signs straight. So negative delta H means exothermic. Negative delta S means
Spontaneous.
no.
No.
Delta S.
Less order.
More order.
Less order. What would be the less order?
Negative delta S, what happened?
More order.
It was more ordered, right? That's what I said. Negative delta G means it's spontaneous. So,
Alright,
So-
negative H.
not hard. The only thing you have to keep straight is the signs.
This is incredibly hard.
No, it's not. The math of the above equation tells us that delta G, or spontaneity, is favored. So how would I get delta G to be negative? Because I want it to be spontaneous. I want the reaction to happen. So it's going to be favored by a negative delta H. Why? Because if I start with a negative, right? Yes? And I subtract something from it, it's most likely going to be negative. Yes? By a negative delta H and a what for my delta S? I want my delta S to be
Positive.
positive, because a negative minus a positive gives me a bigger negative. T always has to be positive. Why?
Because temperature can't be below.
It's Kelvin temperature, right? So a negative minus a positive gives me more of a negative. That's what it's going to be for spontaneity. A thermodynamically favored equation may be very slow. So it still could be spontaneous if the activation energy is high. So a reaction that has a negative delta G may not occur at a measurable rate, even though it's spontaneous. If this is true, the thermodynamically favored reaction is said to be under kinetic control. So it's still spontaneous, it just has to get over that hump. And we're going to do a lab next week over this. But I didn't want to do it today. Here, measurable. Sorry, not enough space to write. So here's the signs. So what does a positive delta H mean for heat? Heat in. Agreed? A positive delta S means?
Less order.
Nope.
More order.
More order.
Got it that time.
Oh no, more disordered.
Oh, no.
Sorry.
You didn't get it that time.
More disordered. So if I have I'm going to rewrite the equation. Delta G equals delta H. I'm going to write it right here. Delta H minus T delta S. So if I have a positive delta H and I have a positive delta S, this would be negative at high temperatures. Agreed? But it could be positive at low temperatures. Yes? So I'm just kind of showing you all the scenarios for spontaneity. Here, positive H means heat in, it feels cold. A negative delta S means it is less disordered. So if I have a positive delta H and I have a negative delta S, right? A positive minus a negative is going to give me more what? Positive. Is this a likely scenario? Are we going to have a positive delta H and is it going to become less disordered? Most likely not. But it's possible. Next one, negative delta H means it is heat going, so release heat, or heat out. Positive delta S is more disordered. So if I have a negative delta H and a positive delta S, that's always negative. It's always spontaneous. And lastly, if I have a negative delta H, which means heat out, I have a negative delta S, which means what? less disorder. At low temperatures, it could be negative, and at high temperatures, it could be positive. So those are just the scenarios out there to kind of think through conceptually. You can also do this with the old school equation we've been using. Delta G at standard equals the sum of delta G of the products minus the sum of delta G of the reactants. Here's the thing. We usually don't do this equation because usually we've already figured out the delta H and the delta S, right? But you can do it that way and you should get the same thing. If delta G is positive, then the reaction isn't thermodynamically favored. That means it's not spontaneous. And if it is 0, now think about this. If delta G is 0, then the reaction isn't favored in either direction. So what would you say that is?
Equilibrium.
That's equilibrium.
Hold on.
Nice job. That's at equilibrium. So if it's favored in either or both directions, if delta G is 0, it is at equilibrium. That is a good place to stop for the day. So Monday,